Oh, good, okay.
Who knows, but that is the work.
Okay, so this is a sort of a different kind of talk. I'm not going to be presenting a lot of new information, although I will present some. But what I'm going to do to start with, at least, is to tell you something of the history of the last 10 years of this project that we started here back in 2012. The idea was to compare cosmological simulations on scales from 10 to the 10 solar mass halos to 10 to the 13 solar mass halos, and initially do it just in dark matter simulations, but then do isolated disk simulations, and finally full-scale cosmological simulations, hydro simulations. From the beginning, Ji-Hoon Kim played a crucial role. It's very unfortunate that he can't be here today. Unfortunately, as one of the organizers of the International Astronomical Union General Assembly in South Korea, he says that he wasn't careful enough and he got COVID, and so he's isolating himself. I think he's recovering now, but he couldn't come. Santi Rocafabrica has played a similar role to Ji-Hoon in the last few years, and you'll hear from him in the next talk. So he's been, along with Ji-Hoon, coordinating this fairly large program. And Clayton Strawn, who you'll also hear from today after Santi, has been coordinating the effort to study the circumgalactic medium in all the simulations. Although that's not what he's going to talk about after Santi, it is what he's going to be talking about on Saturday in our group meeting. So the goal was to create a collaborative multi-code platform to raise the realism and predictive power of high-resolution galaxy simulations. We started with a 6-member steering committee. I'll show what the members were. 2 of whom are present today, namely me and Tom Abel, but several of the others are still involved. There have been a total of 160 plus participants from 60 institutions. We've organized 10 workshops, including the one that's happening on Saturday. We've been having monthly web conferences, most recently using Zoom, and it's been a total of 70 plus of those. The outputs have been shared among all the members, and people are welcome to join if you haven't joined yet. Then you have access to all the outputs of all the simulations, but you can't publish any of them without the permission of the people who actually ran the simulations. And we get together and discuss fairly extensively before we submit the papers. The first paper came out in 2014, and that was a careful comparison of the pure dark matter simulations by 9 different codes. Paper 2, 4 years after the start, 2 years after the first paper, was the study of an isolated disk galaxy, which was supposed to represent a Milky Way at redshift around 1, with about 20% gas fraction. And paper 3 was just published last year, and that's the beginning of this project to study hydrodynamic simulations of a Milky Way mass galaxy. So that carried the project to a redshift of 4 and went through 4 calibration steps. And Santi Rocafabrica is going to talk about that. Now, as you can see, the rate of publication was pretty low, but that's drastically changing. We've had a phase transformation. We have 3 papers in nearly final form that we hope to finalize to some extent at least on Saturday, and several more papers in preparation and a lot of projects that we're discussing. So the project has really picked up speed. Oh, I should mention that it started with sponsorship from the University of California High Performance Astrocomputing Center, which I initiated and ran with a grant of about $2 million from the University of California for 2010 to 2015. we had a little support from NSF and a lot of support from the Department of Energy to the National Energy Research Scientific Computing Center at Berkeley. So these are the three papers: the dark matter only simulations, the isolated disk simulation, and the first fully cosmological simulations. And that's what you're going to hear about from Santi, except it's going to carry them up. This was to Redshift 4. They're now down to below Redshift 2, and we've done careful comparisons to Redshift 2. This was the original steering committee. And there are a lot of different aspects that went into this. The initial conditions were created by Oliver Hahn and collaborators using music, his multi-scale initial condition code. We've used a couple of different updated versions of Grackle, and all the codes were required to use that for heating and cooling. All of the graphs that you're going to see, and many more that I won't show you that are in all the papers, were generated using YT with a lot of help from Matthew Turk, who of course did his PhD at Stanford with Tom Abel. All of this has made it possible to analyze all of the simulations exactly in parallel. And in the process of doing this, we've made it, I think, a lot easier for other groups to use these tools. So in addition to the papers I'm going to mention, there have been at least of order 10 papers that have been using these tools, and I think others in preparation. In addition to the 6 codes that we started with, a lot of new codes have joined, and in particular Gizmo and most recently Arepo. I won't show you today results from Arepo, but we're hoping that in the paper that's going to be studying the hydro simulations to Redshift approximately 2, the Arepo simulation will be added because it's rapidly approaching that. So this was the set of simulations for the first paper, the one we called the flagship paper, the 2014 paper led by Ji-Hoon Kim. And if you look really carefully, you'll start to see slight differences in these codes. And in the paper, the differences are discussed in detail. In particular, the adaptive mesh refinement codes, ART, ENSO, and Ramses, are somewhat different in the structure of the outputs from the particle codes. All this was discussed in detail in the first paper. The second paper was based on the isolated disk simulation. There were 39 plots in that paper. This is one of those plots. That's another one of the plots. Each of those plots had 9 different panels, and sometimes double ties, because they're all comparing all these 9 different simulations. What we found was that if carefully constrained, the galaxy simulation codes agree well with one another despite having evolved largely independently for many years without crossbreeding. And simulations are more sensitive to input physics than to intrinsic code differences. This surprised me. The extent to which the codes, and they're very different codes, actually agreed was, I think, really quite surprising. Here's some examples. So this is the surface density profile of the 9 different codes, the rotation velocity profile, the velocity dispersion profile, so these two go together, and the Kennickett-Schmidt relation. And I mean, there's a span of plus or minus, I don't know, 0.3 dex or something like that, but generally really quite good agreement. And in some of these cases, the agreement is better than 10%. So, but along the way, there was a lot of improvement in the codes and in the analysis. Various errors were fixed. Participants found an optimal set of simulation parameters that make their code best compatible with others. The feedback, for example, that was initially introduced didn't work the way many groups thought it would when they compared with other codes. And adjustments were made and codes were rerun a number of times in many cases. And numerical errors were discovered and fixed in a number of the participating codes. So I think that this project has been a generally beneficial project for the whole community. All of the results from that isolated disk code comparison project have been made public on FlatHub, which is open to very wide use by different groups, supported by the Simons Foundation, the Flatiron Institute, and the Center for Computational Astrophysics in New York City. So we're using it also, and there's also a paper led by Santi Rocafabrica that explains exactly what's in the data, and you click on this and that actually takes you to all the data on FlatHub. Our plan is to put the data from these many different cosmological simulations also on FlatHub, and with all kinds of tools to make it easy to interact with the data. So it's been a 10-year human experiment. It's a one-of-a-kind open forum where numerical astrophysicists can talk to and learn from each other. There is a workspace. It's been updated now. There's this infrastructure, the journal articles, the workshops. This was from one of our meetings, I think this was 2019. The many 70-plus telecons, and these are examples from the first two papers. So this is what we're working on now. There's the circumgalactic medium paper that Clayton Strawn is leading. The CosmoRun 2 paper, so what we're calling these hydrodynamic cosmological simulations is CosmoRun. And this is the second paper, the one that takes us down to around Redshift 2. And then there's also another paper that looks at the CosmoRun 2, but not focusing on the central galaxy, but instead on the satellite galaxies. And these three papers are all in more or less final shape, and we hope to finalize them tomorrow. So this is the place that you're taken to if you click on the AGORA panel, the AGORA tab on the 2022 Galaxy Workshop website. So if you want to find out in more detail what we're doing, just click on that and it's all available. Now, this is actually a figure from the first, the flagship paper. And as I mentioned, we did simulations, pure dark matter simulations, on 10 to the 10, 10 to the 11, 10 to the 12, and 10 to the 13 solar masses. And the simulations were chosen to be very merger full and rather quiescent. The simulation that we chose to do a hydro simulation of, with all the different codes, is the halo with fewer mergers at about 10 to the 12 solar masses at redshift 0. And this is the accretion history. This is the merger tree. And one thing that you'll notice here is that right around 0.33 scale factor, which of course is redshift 2, there's a merger. And that was a problem because not all the codes did that merger exactly at redshift 2. Some did a little bit earlier, some did a little bit later. That's how numerical simulations work. But if you want to compare codes, you have to do it roughly at the same stage. And if you are in the midst of a merger, that's going to mess things up. So Santi will tell you how we dealt with that problem. This is an accretion history that may be rather similar to that of the Milky Way, although there is this merger here at somewhere around redshift 1. Actually, redshift 1 would be here. So it's below redshift 1. It's a fairly large merger, although it's not a major merger. And maybe that's like the Milky Way and Sagittarius. I don't know. We weren't trying to mimic the Milky Way, but of course every dark matter halo is its own story. And this is the halo that we were dealing with. This is the pure dark matter version. Of course, now we're running hydro. So these are 4 calibration steps that were described in Santi's first paper, the 2021 paper. And without going into the details, Santi may tell you more about this. The codes share a common cosmology, the Grackle heating cooling, common star formation recipe, common initial conditions, very similar yields of metals, They keep track of the metals, and they're calibrated and checked to make sure that the results are acceptably close, including the stellar mass. The codes calibrate different supernova. So one thing that's crucially different among all the codes is all the different groups were told, please use a feedback prescription which is typical of the simulations that you're currently doing. So in many respects, the codes are being forced to be as similar as possible, but the feedback is not at all the same. It's quite different among the different codes, and that has very important consequences, as you're going to find out. So different supernova feedback recipes. None of the codes included the effect of AGN. No supermassive black holes were included, but we're only running at this point to Redshift 2. Probably if we tried to run below Redshift 1, we would get into serious trouble if we don't include AGN. The codes did not calibrate the data below Redshift 4. The last calibration step was at Redshift 4. And so Sandy's going to talk about how the codes have been evolving now down to about Redshift 2. At the same time, we're also studying the certain galactic medium in all the codes. And that, as I said, is being led by Clayton Strawn. And then there's also a paper on satellite galaxies, and that's full of all kinds of interesting results. And that, as I said, is also nearly ready for submission. So this is the history of the stellar mass growth. Of course, we know it back before Redshift 6, but this is from Redshift 6 to Redshift 2. And as you see, there's a fairly big difference, about a factor of 5, even an order of magnitude at various redshifts. But at Redshift 4, they're within a factor of 3. And at Redshift 2, they're also within a factor of 3 in stellar mass. So the codes are chugging along, and in fact, some of the codes have now gotten down to almost Redshift 0. But at the moment, we're analyzing all the codes down to around Redshift 1. You'll notice, actually, there's Gizmo, which isn't on this plot, but we have the information. And you'll see that the adaptive mesh refinement codes are just numbered and the SPH codes are just numbered. And that's because we don't release the data publicly until all the groups have agreed. We're hoping that on Saturday we will get agreement and we'll start to release the data publicly. And we'll tell you what the names are of these codes. I mean, which ones are which. But the thing you're supposed to notice here is they're really behaving fairly similarly. So here we did name them because this is published. This is the data down to Redshift 2. And let me start it again. So there's actually a video playing. So this is Redshift 13, 12, 10. And this is the temperature, the dark matter density, the gas density, the metallicity. And remember, all of this was generated by YT. So YT is reading the output of all the codes and generating all these images. And you can use it too if you haven't used it already. Clayton in particular has made it very easy to read any of the widely used codes with YT. This is also from the 2021 paper that Santi led. And these are the results at Redshift 4. That's where the comparison was made in the last calibration step. So again, gas density, temperature, gas metallicity, and stellar density. The galaxies don't look too different, but they don't look all the same either. And the same thing has happened as we've carried it down to lower redshift. So this is now running down to Redshift 2. Actually here, they are named, and here, in addition to the 6 that I was telling you about before, there's Gizmo. But it's marked preliminary. But as I say, we hope to finalize this paper very soon. And you'll hear much more about this from Santi. So we hope to finish up 2+ papers, maybe including the third paper, which would be the satellite paper, very soon. So Santi's going to talk about Cosmo Run 2, in other words, down to redshift around 2. Clayton tomorrow is going to present the details of the circumgalactic medium paper down to redshift 2, which makes essential use of another tool, Trident, which makes artificial quasar absorption lines in many different directions through halos. And so Clayton has been leading that study. And then there's the satellites paper. And this is just an example of all the little satellite dark matter halos from 9 different simulations, including some dark matter only simulations. Now I'm going to show you a few of the slides 5 minutes ago. That's fine. I'm going to show you a few of the slides from the paper that Clayton is leading, although I think actually some of these will be in Santi's talk as well. So what we're looking at here is the greener it is the higher mass fraction in shells, and these are shells at several different radii, and the first little dashed curve is 15% of the virial radius of the halo. And you'll see that all of the codes have most of the mass, at least the AMR codes, have most of the density at around 80 to a little bit more than that parsecs inside where the galaxy is, which is 15% of the virial radius. In the circumgalactic medium, so out at about half the virial radius, the resolution is, for most of the codes, all of the AMR codes, adaptive measure refinement codes, and some of the SPH codes, the resolution is better than a kiloparsec. All the way out to the edge of the circumgalactic medium, at least as we're defining it here, at the virial radius, the resolution is a few kiloparsecs. It's not bad. I should have said, all of these codes are required to have best resolution in the high density regions where the galaxies are forming stars of 80 parsecs or better. So they're pretty high resolution simulations, but not the super high resolution simulations that some groups have been doing. So this is summarizing what I just told you. And the SPH codes have 2 different forms of resolution. So there's also a linear resolution equivalent, which is here, and then a smoothing length. So I realize too much information to take in, and probably in the back you can hardly see. This is a table from the paper. I think this is from Clayton's paper. And this is describing the stellar feedback, supernova and metal production model, the effective metal yield, and various runtime parameters for each of the codes. And of course, in the final version, the codes will be identified. But the important thing to appreciate is some have radiation pressure, kinetic as well as thermal feedback from stars, and other codes don't. So the key thing to appreciate is that the feedback is different in every code. So that's going to result in very different metal distributions. So this is a plot from the paper Santi's leading. This is the metallicity, the number density, temperature, and radial velocity. And these are the SPH codes, these 3 on the right. These are the AMR codes. And there are substantial differences. The AMR codes kick out more metals into the intergalactic medium. They have stronger velocities, and they have more substructure in the halo. The SPH codes have a more well-defined effect at the virial radius, which is the circle in each code. And of course, they're not exactly the same because the masses are not the same, and the different, I mean, they started out, dark matter was all the same. But once you run with hydro, you get pretty different results. This is another way of looking at what's happening to the metals. So red is the total metals, and within a factor of 4, the metal formation is the same, so it's similar. Remember, the stellar masses are different by about a factor of 3, so you shouldn't expect the metal production to be the same. But where the metals end up is really quite different. In the SPH codes, the vast majority of the metals remain in the galaxy, with 10% or less in the circumgalactic medium, and even less in the intergalactic medium. two AMR codes have roughly equal fractions in the galaxy, the supergalactic medium, and the IGM, although one has a distribution similar to the, okay, I'm coming to the end. One more plot that Clayton will explain in detail on Saturday, so this is based on lines of sight through the codes, through the simulation boxes at redshift of around 2. And this is increasing ionization energy, silicon 4, carbon 4, oxygen 6, neon 8. And the main thing that I want you to take away, each different color represents a different simulation. And although it's interesting to look at all the different simulations and how they behave, another thing that you should notice is how different the simulations are. So my message based on the isolated disk simulation is how similar all the simulations were in many respects. In the circumgalactic media, how different they are in many respects. So tomorrow we're going to be studying all of these things, and then also the satellites project. One of the things we've learned from the satellites project is that all the codes are equally well solving the missing satellite problem. There is no missing satellite problem. They are killing many of the pure dark matter satellites, especially the lower mass ones, and not turning them into observable satellites. It's looking quite consistent with the observations. There are a number of other projects that we're discussing, including one that Yves Ravat has been leading, and we hope to make substantial decisions in our meeting on Saturday as to which directions to pursue. And there are lots of interesting choices to make. So that's all I wanted to say. I think I'm ending right on time. And join AGORA if you haven't already. It's an opportunity to see what all the different codes are doing. Of course, you have to agree when you join that you're not going to publish anybody's results unless they approve that. But it's a community that has been quite useful, I think. Especially for younger people. There's no charge, and you get lots of benefits. Okay, thank you.
So thank you, Joel, for this very nice presentation. Questions?
Hi. Perhaps to some extent this will be discussed during the meeting tomorrow, but I wonder, especially when you start comparing CGM properties and stuff like where the metals are in the CGM or the IGM, those are results that I'm willing to bet good money are not converged in any of the codes. So we're comparing not only a lot of uncertainties hidden in the numerical physics, but hidden in the subgrid physics, but things that are almost certainly not numerically converged in any given code, and the convergence properties in the different codes are likely very different. So I wonder what, in those types of metrics, what exactly is the key goal that we would hope to get from here?
So I'm not sure that it's true that that these are not completely converged. Notice that we're studying these fairly high ion states. I would totally agree with you that the low ion states, magnesium 2, silicon 2, there's no hope. Because those are found in fairly small, dense regions where they're prevented from being further ionized by being surrounded by a lot of neutral hydrogen. These regions are probably a few kiloparsecs in size, and our resolution is simply inadequate to deal with that. But it's likely, we think, that the high ions are more broadly distributed, and maybe some of these results are potentially interesting, at least in broad brush. I think the thing that I emphasized is how different the codes are. And that, I think, is probably going to be true even if we rerun the codes at higher resolution, which is one of the things we're considering doing. Running at much higher resolution, and of course that's the way to tell, at least to some extent, if they're converged. But it's a good point, and I certainly wouldn't trust this for the low ion states.
Very nice. You mentioned reproducibility, and it's hard to judge, reproducibility when, people use different feedback recipes and all that stuff. One thing you could do,
They're certainly not but notice that the different feedback recipes were used in the isolated disk comparison, and there the agreement was spectacular.
Well, how do you judge spectaculars? We're getting at. So one thing I was wondering, have you considered the following? Use the same simulation, same code, everything, go back to the initial conditions, set up the initial conditions, just change a different random numbered seed and run the simulation.
Great
if you
idea.
do that, then you have a standard to which you can compare reproducibility and all that stuff. So
It has been a problem to get all the codes run down to the same Redshift and so on. And asking people to run many more examples may be difficult in the context of the simulation. But doing this genetic change, just changing phases, those would be great things to do if we had unlimited resources, human as well as machine.
Yeah, I just wanted to underscore Joel's point about what a fantastic community AGORA is. I'm from a small liberal arts college in the Northwest, Reed, and I joined AGORA very late, but it's been a real godsend for me and my students because it's such a fantastic community. The Zoom meetings that we've had during the pandemic were absolutely fantastic, and my learning in astrophysics coming to it late in my career has been really spectacular. So I think his point about opportunities for young researchers is should be taken real seriously. Thanks, Joel.
Thanks, Johnny.
Yeah.
Okay, so I think that we can stop here and go for coffee or continue the discussions over coffee, and we'll start again at 11.
Great.